Hello, ladies and gents, and welcome back. And we are continuing on with the binomial distribution. Here we're taking a look at B4. And just to remind you, we were looking at this dice experiment here, where we're asking the question, if you had 10 dice and rolled them, and a 1 was considered to be a success, and any other number, a 2, 3, 4, 5, or 6 was a failure, then we asked the question, well, what's the probability of getting 4 successes in 10 rolls of the dice? And so we said, here's one possibility, that the first 4 are successes and the last 6 are failures. And so that would be 1 6 to the 4th power times 5 6 to the 6th power. But we also said that those 4 successes doesn't necessarily have to be the first 4. They could be any 4 dice in those 10. And therefore, there is 10 choose 4 different combinations that would give us 4 successes and 6 failures. The generic formula for probability, a binomial probability, is this guy here. The probability of getting x successes in n trials is n choose x times p to the x times 1 minus p to the n minus x. The properties of a binomial experiment are these. Number 1, the experiment consists of n identical trials. What that means is that a die is a die is a die, right? So every die is the same as any other die, really. And the same with flipping coins and so on. What's going to be interesting here, though, is that we're going to be using the same thing when we're talking about sampling people. And you might say, well, obviously people are different. But in terms of the thing that we're measuring, we're going to say, well, a Canadian is a Canadian is a Canadian, or a student is a student, right? And we'll actually be looking to see, well, are there differences between the students because of some other factor? But we'll actually look at, a person is a person. That's the idea here. Each trial has 2 possible outcomes denoted a success and failure. This is really definitional for a binomial distribution. And that's the main thing here, is you've got successes and failures here. Number 3, the probability of success, denoted P, is the same for each trial. So if you're talking about rolling a die, every die has a 1/6 chance of ending up with a success, which is a 1. If you're flipping coins and you're talking about a head as being a success, then there is a 0.5 chance of getting a head. And then number 4, each trial is independent of the others. So when we're talking about rolling dice, it means that the dice are not affecting each other. When you're flipping a coin, of course, they're not, what you got before doesn't have any bearing on what you're going to get in the next flip. When we're talking about sampling people, it's the same thing. As long as the sample is big enough or spread out enough that they're not influencing each other. So if we're talking about phoning people up and asking, hey, do you think that Elvis is alive or not? That's actually a binomial problem. A Canadian is a Canadian. They're either answering yes or no, and they're spread out enough that they're not influencing each other. That would be different than if we, say, did this in class, where I said, hey, put up your hand if you believe in Elvis. Well, you look around and you're influencing each other, so there isn't independence there. The binomial distribution looks like this. And so if you take a look at this graph down here, it looks pretty much like a histogram, doesn't it? So on your x-axis, what you've got is all the different values of x, 0 to 10. This one is for the dice experiment. And then on the left-hand side, you've got P of x. The thing to remember about probabilities is that they are, an objective probability is a relative frequency in the long run. Remember, back at the beginning of Unit P, Carrick's experiment. So it's really similar to F over N when we were looking at that in graphs. But we're talking about, theoretically, if you were to roll 10 dice an infinite number of times, then this is the probabilities that would happen here. So we're saying here, and which makes sense, is that if you roll 10 dice, you're likely to get some ones. And so it says that it looks like about a 17% chance that you would get 0 ones, that there would be about a 34% chance of getting 1 1, and the rest would be failures, and so on. It's really hard to get 7, 8, 9, 10 ones in a die, in a roll of 10 dice. But it's not impossible. So that's important to notice, that these are not actually 0. It's just they round down to 0 on a graph here. The other thing I want you to notice about this graph here is, and I talk about this in the lab video as well, is that there's actually no thickness to these bars. You actually jump from 0 to 1 to 3 to 4 to 5 to 6. You can't have 3.5 successes. You can't roll the dice and get 3.5 ones, right? So that is what we call a discrete distribution, where we're dealing with integers here, and so you have 0, 1, 2, 3, 4, 5, 6, all the way up to, in this case, 10 possibilities, but you can't have fractions. Okay, what I've got down here is one which we're going to kind of skip over. I just want to tell you what it's about here, and it's something that you might want to give this a try yourself. So I'm going to assign this actually for homework for you to try yourself here, and it's the following question here. If you were to have a whole bunch of people, theoretically an infinite number of people, but even say the number of people in our class, if everybody was given 10 coins and you were asked to flip them all, or I guess another way of saying it would be 1 coin flipped 10 times, right? It would be the same kind of thing. So 10 flips of the coin. The question is, how many of you do you think would get no heads? So all tails. How many of you would get 1 head? How many of you would get 2 heads? How many would get 3 heads? And so on. So you might want to think of that. Think of, let's say we had 100 people here. And so out of 100 people, how many do you think would get no heads? So 10 tails. And just write that down here. And then add them all up, and of course they should add up to 100. The other thing to note here is that, would you agree that the probability of getting 0 heads should be the same as the probability of getting 10 heads, right? Probability of getting all tails should be the same as getting all heads. Similarly, the probability of getting 1 head should be the same as getting 9 heads. So you see that there's a symmetry here when we're talking about rolling dice. Anyways, give that a try, and then we're actually going to calculate the real probabilities using a binomial formula. If this were a class, what I'd do is I'd actually hand out coins, and we would flip the coins. And that's something we could do online, but given the time, actually, we're not going to go through that. So you will see the answer here, but it's probably worthwhile actually coming up then with your guess as to what the frequencies are, and see if you're close to the actual probabilities when we calculate them by formula. All right, let's continue on here. So calculate all 11 of the p of x's for the coin tossing experiment. Let's take a look at what we've got here. In the coin tossing experiment, we had n is equal to 10 dice. No, 10 coins. Sorry, the next one is the dice experiment. So we've got 10 coins. P is equal to 1/2, and that's going to be the probability of getting a head. And that's going to be on a per coin basis. So in binomial language, we would say that we have 10 trials, and P is the probability of success per trials. Can't even read that. Trials, and the probability of success per trial. X is equal to the number of successes, which in our particular case then is heads, in 10 trials, which is 10 coins. The important thing to remember is that X can take on values of 0 up to 10. A common mistake is to forget about the 0. So I'm going to do a couple of calculations here, and then we can write them all out here. Let's take the probability that X is equal to, let's say, 2 heads. So if you flipped 10 coins, what's the probability that you got 2 heads and you got 8 tails? Well, the formula that we have here is n choose x times p to the x power 1 minus p to the n minus x power. In our case then, that would be 10 choose 2 times p, which is 0.5, or 1/2, to the x power times 1 minus 1/2, which is also 1/2, to the 10 minus 2 power, which is 8. Okay, so that's going to be 10 choose 2 times 0.5 to the squared times 0.5 to the 8th power. Now I know that you could put these together and just say that it's 0.5 to the 10th power, but in most problems your p is going to be something different from 0.5. Like in the dice rolling experiment, it was 1/6, so it'll be 1/6 and 5/6. All right, let's do a calculation here. Okay, so we're going to have here 10 choose 2, so we're going to start with this guy right here. And 10 choose 2 is 10 factorial over 2 factorial, 8 factorial. And that's going to be 10 times 9 times, are you okay with me just putting down 8 factorial here? Because that's 8 times 7, 6, 5, 4, 3, 2, 1, over 2 times 1 times, again, 8 factorial, which is 8, 7, 6, 5, 4, 3, 2, 1. And so we could just do some crossing out here. And so we'll end up here with 45. So there's 45 different combinations that would give us 2 heads and 8 tails. And then 0.5 squared is going to be 0.25. And then 0.5 to the 8th power is 0.0039063. And so if you multiply all of those together, then you will get 0.0439. So about a 4% chance of getting 2 heads. All right, let's try another one here. Let's do the probability. Let's do actually the first one, the probability that x is equal to 0. And I did another one first, although 0 is the first number. I did another one first because 0 is using 0 factorial, which gets a little goofy, that's all. It's actually pretty simple to do, but I think it's easier to understand when you take a look at a number like 2. But this would be, this would be 10 choose 0 times 0.5 to the 0 power times 0.5 to the 10 minus 0 power. Now, 10 choose 0 is 10 factorial over 10 factorial times 0 factorial. And that's just equal to 1. So I told you in the last video here that 0 factorial is 1, and then of course the 10 factorials cross out, and so you end up with 1 times, if you remember your math, anything to the 0 power is also 1. And so that just leaves us with 0.5 to the 10th power, and that turns out to be about 0.001024. I think that's what it is. Let me do a quick check here on that. It's 0.0009766. That's better. Anyways, that comes out to basically 0.0010. So 1/10 of a percent here. That's what that is. So we're going to come up then with a probability chart here. I don't have a lot of room down here, but I'm going to squeeze it in here and say, here's our distribution, the x's and the p of x's, like this. And x takes on values like this. Oop, I'm going to go over to the next page here. And we figured out that this one was 0.0010. I'm taking this to 4 decimal places because you'll see in a bit here that that's actually what our table shows us, but we'll see that in a bit. Probability of 1 is 0.0098. Probability of 2, we calculated this by hand as well. This is 0.0439. Probability of getting 3 heads is 0.1172. And then we've got 0.2051. Probability of getting 5 heads is 0.2561. And then the numbers actually, this is symmetric. The probability of, so we just go back down again. Probability of getting 4 heads and 6 tails is the same probability of getting 6 heads and 4 tails. So we just actually go back down with the probabilities like that. And if you add all those up, you'll get 100% like that. So that's what we call the probability distribution for x. And in this case then, the binomial experiment of the 10 coins. So what I like you to do is the same thing then for the 11 p of x's for the dice experiment. So in that case then, n was equal to 10 dice. P is equal to 1/6, which is the probability of getting a 1. Anything else is considered a failure. And then you should come up with a probability chart here that looks like this. And x will go, same as with the coin experiment, it'll go from 0 to 10 here. But the probabilities are going to be different because you've got a different p. So I'd like you to do that one for homework, and we will take that up in class there. Last thing here is it says probability distribution is referred to as a discrete distribution, meaning that the outcomes are counted rather than measured. So we count the number of successes. Moreover, any distribution, probability distribution, must adhere to the probability axioms back in unit P. And so for a binomial distribution, this is what we've got, is that all of the probabilities are between 0 and 1. So if you take a look up here, they're all between 0 and 1. In a binomial experiment, some outcome must occur. That just simply means that if we roll or flip 10 coins, then one of these possibilities has to occur in terms of the number of heads that we get. And then finally, all of the outcomes must be mutually exclusive and collectively exhaustive. Remember, mutually exclusive meant that if in your experiment you tossed 10 coins and if you got 4 heads, it means you didn't get 5 heads, right? You didn't get 7 heads or 8 heads or 2 heads. You got 4 on that particular experiment. So you get one of the outcomes. And collectively exhaustive means that if you add up all the probabilities, it comes to 100%. So they exhaust all possibilities. There's no other possibility than the ones that we've got listed there. So those are the axioms there that we've got. So we can go check, check, check for all of the different ones for the coin experiment. When you do the dice experiment, it should be the same here. These probabilities will add up to 1 when you do those. And that's where we will end there. We'll talk about how to use tables next.